Hello and welcome everyone to this series on linear regression. Today we'll be studying about gradient descent, which is an algorithm, and I'm Divya Thakur. The first question is, why gradient descent? Why are we studying about this? So in the previous video, I discussed about the univariate analysis of also known as simple linear regression between heights and weights of people. This is what I plotted as my regression line that was trained on the training data set, and this is what I got as the predicted y with my first coefficient and second coefficient respectively. Also, the mean squared error of such kind of a regression was 1.62 when tested on the test data set. If you want to check out the heights and the weights video, I have attached a link in the description, so you can click on that. And also, if you don't know what mean squared error is, I'm also attaching the link to the same, so you can watch those videos. So our goal is to minimize this mean squared error, right? And the regression line that we are getting right now is because we have trained this model only once. So the intuition behind this gradient descent is that if you are painting something and at first go you're not able to make it perfect, then in the successive attempts, that is in the second or the third go, maybe you can replicate the same painting. And similarly with cooking, so if you have cooked a dish and it's not up to the mark, then on the second try and at the third try, maybe you can get that taste, the desired taste. So same is with our machine learning model, with the regression model. So let's understand this more. So what actually is gradient descent? So this gradient descent is actually an optimization technique. It's an iterative process. So this technique's goal is to minimize the mean squared error, our loss function. So it lessens that up for a model. How does it do that? It's an iterative process. So if we have theta 1, theta 0 and MSC as our first coefficient, second coefficient and mean squared error value during our first iteration, so we are talking about computers, so let's call it I equals to 0, the first iteration. During the second iteration, this gradient descent algorithm will minimize this MSC, will minimize this mean squared error. And during the third iteration, it will further minimize, further lessen down MSC. So in these iterations, MSC now comes to be known as cost function, also denoted by J. So it's no longer a loss function, but the cost function, because we are having it iteratively. We are lessening it down iteratively. So suppose you are a mountaineer standing at the top of the mountain and you desire to descend at the bottom of this mountain to the valley. So how may you do that? If you travel through these places which are solids, then you may encounter a forest and you get stuck. So the wise decision will be to follow the slopes and get down to the bottom of the valley. So during the first iteration, you can either go down this slope or this slope. Then once you reach the destination point, you can again try going down the slope, which can be either this one, or this one. And finally, you can try either of these slopes to reach the bottom of the valley. So the goal behind this activity of ours is to minimize, that is, to have the minimum distance, the minimum slope distance in order to reach the valley. That's our goal. So in terms of machine learning, we want a minimum cost function at the end of our iterative process. So the direction that this mountaineer is following over here are the slopes of the mountain. In a similar fashion, we are gonna be following the derivative or cost of our cost function in order to reach the minimum value of this cost function. So we are gonna be following the derivative of our cost function. So see, so this is our cost function over here, and in order to reach this minimum value, because we are starting from over here, so our slope must be negative, then it's again a negative value, again a negative, and slowly it's reaching the zeroth value, close to zero. If we started from here, that means our slope is positive, so we would have traveled all down to here in order to reach zero. And in this process of a cost function lessening itself down to zero, the regression line is fitting better and better with this kind of an algorithm. Now the next important parameter is learning rate. So learning rate is nothing but the steps, the size of the steps that we are taking in order to reach the minimum or the bottom is the learning rate. So for instance, we can either cover more area with larger steps or a higher learning rate, and we are at the risk of overshooting the minima. So let me show it to you. So if we are having larger steps, like over here in just one step it got down to the minima, then we have the risk of overshooting the minima. We can either skip it also and go farther away. So it's best suited not to take a larger learning rate. Similarly, it's best suited not to take a very small learning rate like over here 0.1, because ultimately it's taking a large number of steps, which is 81 over here, in order to reach minima. So like this is the optimal solution, wherein the learning rate, according to this problem, this is the optimal. The learning rate is set to 1 and the steps taken are 6. So in order to calculate how do we reach the minimum cost function, we have to take into account these things, which are the parameters. So over here in this video, I'm calling my theta 1 to be m, which is the slope of the line, and theta 0 to be b or bias, which is the intercept of the line. So don't get confused with theta 1, theta 0, m or b notations. It's just one and the same thing. So we have to keep into account the changes in our parameters. So with every iteration, our parameters are gonna be changing, and the parameters will change in accordance with the slope of the cost function, or the derivative of the previous m. So we'll see how these parameters are changing uh, at the end, but let's now focus on the cost function, which is the average sum of the predicted y values minus the given values in our test data set. So this squared function over here, which is the error function. So let's ponder upon this cost function. So in gradient descent, this cost function is nothing but j m comma b, and this is the notation, that is the average summation of the error squared. So we'll concentrate upon cost function right now. So let's, because this cost function is a function of m comma b, so let's now take partial derivative of this function with respect to m and with respect to b, which is nothing but taking partial derivative of the cost function with respect to theta 1 and theta 0 respectively. So this square value after taking derivative will become 2 times error over here, and we'll be left with the derivative of this error function with respect to m, and we should have an n over here as well. So 2 upon m multiplied with error that we got and partial derivative of this error with respect to m. Similarly, 2 upon n times error and partial derivative of this error with respect to b. So let's concentrate upon this thing, which is partial derivative of error with respect to m and partial derivative of error with respect to b. So what are these values? So error is nothing but predicted value minus the observed value in both the cases. So predicted value is nothing but at each step the prediction is based on m and b values. So mx plus b is the predicted value over here minus y, and similarly mx plus b minus y. But in this case, partial derivative of m, this x is a constant, b is a constant, and y is a constant, but only m is varying. While over here, m is a constant, x is a constant, y is a constant, and b is a variable with respect to partial derivative of b. So let's see what will happen. So these constants, the partial derivative of these constants will be 0, and of this mx will just be x over here. Similarly, the partial derivative of mx, because both of them are constants, will be 0, and of y also will be 0. So you are left with partial derivative of b with respect to b, which is nothing but 1. So if you remember, the partial derivative of a cost function with respect to m is nothing but 2 upon n times error times this function, error function with respect to m, and similarly error function with respect to b. So this becomes cost function, the derivative of cost function with respect to b becomes 2 upon n times error times our learning rate, because this thing, del error of del b, is nothing but 1. So 2 times error times 1. So 1 is then being multiplied with learning rate. And similarly, cost function with respect to m becomes 2 times error times x from over here times learning rate. So why am I multiplying this whole function with learning rate? That's because learning rate determines how large a step to take, and it should be multiplied with every partial derivative of the cost function, while this term over here, which should have been 2 times error times x upon n, determines the direction to minimize this error. So if it gives us a negative product, it means that we should uh, be on the left of our minima, but if it gives us a positive product, it means that we are towards the right of the minima. And now let's concentrate on our parameters, which are nothing but m minus del m, and over here it's b minus del b at each iteration. So del m is nothing but error times x times learning rate, and del b is nothing but error times learning rate, where m1 and b1 are the next position parameters, that is of the next iteration, and m0 and b0 are the current position parameters. So in our code, we'll be seeing Iris setosa, which is a type of a flower. So it has got both these petals and these big sepals. So as you can see in this picture, so this is the width of the sepal and the length of the sepal. And similarly, this is the width of the petal and the length of the petal. So we have all these terms here: sepal length, sepal width, petal length, petal width, and the species we have is of this flower, which is Iris setosa. So we'll see, if we train our model just once, then what is the mean squared error, and if we train a model with respect to this gradient descent algorithm, that is through an iterative process, then what happens to the uh, mean squared error, that is a cost function, with gradient descent and without gradient descent in Jupyter Notebook, and we'll see our results. Over here I have a Jupyter Notebook wherein the first cell I'm importing these libraries, which is NumPy, Pandas, and matplotlib.pyplot. Additionally, I'm giving it a style of 538. If you want to use any other style, you can refer to these available styles over here, and I have chosen this one, 538, for my plots. So we have to import the Iris dataset. So I'll be using the pandas retos CSV because my dataset is in the CSV form. And let's view the first 5 columns of this data set. So we have the sepal length in centimeters, sepal width also in centimeters, petal length, petal width, and the species is Iris setosa. So let's see the total number of rows and columns that a dataset has using the shape attribute. So it has 150 rows and 6 columns that we can see: ID, sepal length, sepal width. So these are 6 columns in total, and we have such 150 observations. So to make a training dataset, we'll choose the first 120 species out of the given 150 species. So my X I have taken as the sepal length in centimeters, and then I'll be choosing the first 20 entries with this ilog function, that is 0th observation included and 120th observation excluded. And then I'll extract the values and reshape it into a row vector instead of a column one. So let's analyze the relationship between the sepal width and the sepal length of Iris setosa. So over here I have plt.plot with respect to our x and y. So this is our training data set. Now let's train our model without gradient descent, that is a linear model, a linear regression model. So from scikit-learn I'm importing linear model, and from its metrics I'm importing the mean squared error, that is a loss function. So let me create a linear regression object. And then train this using the fit function and passing in the x and y. So let's see our model's coefficient using the regression variable and also the intercept. So we have the coefficient as this and the intercept as this. So let's plot the regression line against our training data set where data points are present in a scattered format. So I'll just pass in the x, and my y this time will be the predicted y. So I'll extract this REGR, the slope. So because this is in this kind of a format, so I'll just extract the value. So it's 0 and then again a 0 because it's in a double array, and I'm gonna be multiplying it with x and adding the bias or the intercept, which is nothing but regr dot intercept underscore and also the first entry. So because we are performing linear regression, we just have one entry each over here. But if we had multiple regression, we could have multiple entries, and so this becomes important. So these are our data points, and this is a regression line. So let's see what our mean squared error is. It's 7.61. Over here I have the gradient descent functions. I have taken the iterations to be 100 and defined the m current and b current values to be 0. To the gradient descent function I'm passing in the x and y, my trained data sets, the training data sets. I've declared n to be the length of x. You can also write it to be the length of y because they have the same length, which is 120, and learning rate is 0.02, which is I have taken. You can also with trial and error have a different value. Then next I have defined these three lists, m, b and cost function, to gather the values of m, b and cost respectively during each iteration. So I'm running this for loop for 100 times for I in range iterations. I have declared the y predicted variable to be equal to m current times x plus b current. So initially this is 0, both the values are 0. So my cost variable is equal to 1 times n, 1 upon n times sum of y minus y predicted whole square, and md, the parameters, the md which is the partial derivative, the error with respect to m is minus 2 by n times sum of x times y minus y predicted, and bd is equal to minus 2 by n times sum of just y minus y predicted. Then these values of m and b are also changing, so I've used the compound subtraction here. This can also be equal to m current equals to the current value minus the value that I'm getting by multiplying my learning rate with md, that is partial derivative of m, partial derivative of this cost function with respect to m. And same goes for here. Then next I'm printing all these values mb cost during each iteration, and also appending them to my list mb and cost function and returning this list itself. So to the same variable names, I'm storing these returned values while calling the function. So let me run this function of gradient descent and then make a call to this gradient descent function. So I have this print statement running over here, and my values getting stored over here. So you can see during the first iteration my cost was 9.6, and during these 100 iterations the cost value decreased, and at the 100th iteration it's 0.401. So let me show you the plot of this cost function. So I'll just do an np.arrange of my iterations with respect to cost function, the list that we just got. So these are the iterations, and this is the cost. So cost gradually decreased from 9 to 0 as the number of iterations increased. So this is, so now let's print the mean squared error with respect to our x and y. So this time the y is the last value that I'm getting from the m. I can also do it 99 times x plus the last value from the list of b. So let's print this out, and this is 7.16 as opposed to 7.61 when we just did a simple linear regression. So gradient descent has greatly reduced our cost from 7.61 to 7.16. And now let me plot this against our training dataset, what our regression line looks like. So I'm just grabbing the y from over here, and let me give it the color of black for this regression line. So I'm just plotting the regression line while I'm scatter plotting these data points. So this is how a regression line looks like, and let's compare the regression lines that we had without gradient descent and now with gradient descent. So without we had this, and with gradient descent we're having this. So without is in red color and with is in green color. So when we run the cell, so as you can see, these are two different regression lines that are fitting, and both of them also have different mean squared error. So this is all, and I hope you understood the basics of gradient descent and how it can be useful while doing linear regression. So that's all. Thank you for watching.